Nowadays, a large amount of astronomical observation evidence has confirmed the existence of dark matter and dark energy. Dark energy determines the expansion of the universe, and dark matter is the matter that holds galaxies together. Although we know that dark matter is out there, will we ever be able to see it? Dark matter is a form of matter that exists widely in the universe proposed by astronomers to explain many observational data. This kind of matter must meet two conditions. It needs to provide the same powerful gravity as ordinary matter. In addition to gravity, it cannot interact with ordinary matter and be directly observed by astronomical observation equipment. These two reasons are why it is called dark matter. Dark matter accounts for approximately 84% of all matter in the universe, and the remaining 16% is ordinary matter that we are mostly familiar with. According to the current mainstream model, it is assumed that dark matter particles are supersymmetric particles with a mass of 100 gigaelectron volts, or GeV, the mass of about 100 protons. This would mean the density of dark matter particles all around us is about 5,000 per cubic meter. However, even with the most sensitive detection equipment on Earth, it is still difficult for us to catch its trace. So, is there a way for us to see how dark matter is distributed in the universe? Supercomputers make this possible, and N-body simulation are the eyes that allow us to observe how dark matter forms structures on different scales in the universe. Using Newton's equation, we can easily give precise analytical solutions to the equations of motion of any two particles under gravity. For three or more particles, the so-called three-body or N-body problem becomes a lot more complicated, and it is impossible to obtain a general solution through analytical methods. But after we numerically analyze the gravitational force between n particles, we can calculate the motion equation of the particle within a short period when the path of the particle is approximately a straight line, and then recalculate their mutual gravitational attraction after obtaining the new positions of all particles. By continuously iterating this process, the evolution of the n-particle trajectories can be obtained to accurately simulate the nonlinear evolution process of these particles. This is the N-body simulation method. After ignoring the other forces of a small amount of ordinary matter, the N-body simulation method is a very ideal way to obtain the movement and distribution of dark matter in the universe. Through the movement of these N particles under gravitational force, we can now see the structure they finally formed. Of course, to prevent particles from running out of the simulation box, we need to assume that the boundary of the simulation box is periodic. That is, when the simulated particles run out of one side of the box, they will re-enter the box from the other side. If we set the original conditions in the early universe, for example, the age of the universe is 100 million years, and then evolve to the present, 13.7 billion years, then the evolution of dark matter in the universe can be obtained. However, limited by the computing power of the computer, the N-body simulation also has a limit on the total number of simulated particles. The total number of simulated particles that can be simulated by the largest supercomputer at present can only be about 10 trillion, so the accuracy of the simulation of the entire universe will be restricted. If we want to understand the formation history of more subtle structures in a certain region of interest in cosmological simulation, we need resimulation technology. Resimulation technology can perform a high-precision simulation of the part of the universe again to analyze the distribution of dark matter on a smaller scale. In the 1980s, limited by the computing power of computers, people could only use a few particles to simulate the evolution of the universe. But even so, the N-body simulation still shows its power. When astronomers are hesitant about whether neutrinos are candidates for dark matter, the N-body simulation answers. With neutrinos as the hypothetical dark matter, the structure of the universe and the structure of the galaxy survey counts obtained at that time was very different. This result also eliminated the popular dark matter candidate at the time. With the improvement of computing power, we can use more particles to simulate the formation of these structures. Numerical simulation technology has contributed greatly to the process of helping the cold dark matter model to be established as the standard model of the universe. In 2005, the completion of the MILLENNIUM simulation made us believe that we have a complete and clear picture of the understanding of the large-scale structure of the universe. As shown, we see dark matter forming a bright network structure formed by many high-density nodes in the universe that are connected. These nodes are called dark matter halos, or dark halos for short. These huge nodes are connected by many filaments and sheets. The area enclosed by these filamentary or sheet-like structures are called voids. If all dark matter can be seen by us, then our universe will be a network-like structure. Without supercomputers, it may be difficult for us to see this at all. So, that is all for today's video. Thanks for watching. If you enjoyed our video today, please make sure you hit the like button and don't forget to subscribe to our channel for more interesting content just like this. Also, let us know your thoughts in the comments section below. We will be back very soon with another brand new video, so stay tuned.